The Rust programming language was initially developed a bit over 10 years ago by Graydon Hoare and others while at Mozilla. The 1.0 release was about 5 years ago, and the language and community around it have grown since. The goal was to create a language that could be used for the same types of problems as C++, but without all the issues of memory safety and the challenges of managing that memory. Languages like Java address the memory safety issues by using garbage collection. Pointers can be freely shared, but there is an overhead needed to figure out what memory is no longer used. In Rust, programs that don't make use of the unsafe backdoor shouldn't be able to cause a seg fault. Rust manages this by introducing the concepts of ownership and borrowing. Ownership simply states that every entity managed by the program has a single owner. This owner may be a particular part of the code, or it may be a field in another data structure. The ownership can be moved, but the old location is then no longer valid. References to these items can be borrowed, and the correct use of both ownership and borrowing are strictly checked at compile time. Although I don't have that much time in this presentation to go into much detail about Rust's concept of borrowing, I think it would be helpful to give a few examples. This first example creates a local variable in a function foo and passes a reference to that variable to bar, where bar can print the value of the variable. This isn't very different than what could be done in C or C++. However, the compiler enforces that this reference to A can never be used beyond what the variable itself would live. So if bar were to try to store this reference somewhere, or if foo tried to return it, the result would be a compile error. So in addition to regular references, we can also have mutable references. Rust is more strict about mutable references in that any given place through the execution of the code, there can only be a single mutable reference to something. If we tried to use a non-mutable reference to A while this mutable reference were live, it would result again in a compile error. Now this next example shows a data structure where we have a method that returns a mutable reference to something inside of that struct. The compiler is able to determine that the mutable reference to the inside of the struct also means that there's a reference to the struct, and is able to restrict other references to the struct. Now, this can sometimes be a bit clumsy if you need to have references to different parts of the same struct, and is one of the aspects of Rust that makes it somewhat more difficult to learn than a lot of other languages. However, although something like C or C++ lets you fairly arbitrarily take these kind of references, it's also fairly easy to do in an invalid way. Now, because not all programs can be expressed with these more strict rules about ownership and borrowing, the Rust standard library also has types for shared references, including both single-threaded and thread-safe reference-counted pointers. Another aspect of the borrow checker is that the compiler is able to ensure thread safety across the sharing of data. Because of this checking, and the increase in the safety and security of the code, there is a growing interest in the Rust language, and adoption by numerous large players. This brings us to MCUboot. MCUboot began as the bootloader for the Minute real-time operating system, which was developed by Runtime.io. I, David Brown, working for Linaro, ported this bootloader to Zephyr, and this code is now used in other places as well, such as the bootloader for the Trusted Firmware M project. This bootloader is written in C, with some support tools in Python and Go. The purpose of MCUboot as a secure bootloader is to establish a cryptographically strong root of trust in microcontroller devices. It validates digital signatures on images before running them, as well as validating signatures on upgrade and before installing these upgrade images. The most complicated operation that MCUboot performs is with an update method known as swap. The idea, which may sound simple at first, is to take images in two separate areas of flash known as slots and exchange them. And this has to be done in such a way that if power is lost during the operation, it's able to recover and complete the swap. We currently have two variants of the operation, and a third is under development. Now there's other configuration choices available, such as one known as direct execute in place, where the code's not moved, but linked to run at the correct address. In addition, it can also be configured to load the code from flash into RAM, although there's many microcontrollers that don't have enough SRAM to really be able to do this. This swap process is fairly complicated, and is crucial that it be correct. It's the only part of MCUboot that modifies persistent state. It modifies flash, and if it goes wrong, the end result is usually an unusable device or a brick. Another reason it's so important that the swap code be correct is that MCUboot itself is difficult, if not impossible, to upgrade in a deployed device. For this reason, we attempt to place as little functionality as possible in the bootloader, but being able to safely and securely install an upgrade is part of this core functionality. While I was porting MCUboot to Zephyr, I began to realize that of all of the parts of the code, this swap operation was the most difficult to test. Because power loss can occur at any time, really testing this code would require causing a power failure at any stage. Testing at this level is pretty much impossible on real devices. Instead, I chose to write a simulator and test framework to test this. Based on some past experience, as well as some of the advantages of Rust, we decided to implement this simulator in Rust. The simulator attaches to MCUboot at the API level of calls to the flash driver, which primarily consists of read, write, and erase. And writing this in Rust gives us some pretty immediate advantages. The Rust language ecosystem already has a test framework which supports running multiple tests in parallel. Because of the ownership and borrow checker in the compiler, many types of bugs that would be difficult to find in the simulator can now be found at compile time. Now, the main challenge of doing this was handling the mismatch of calling between Rust and C. Turns out it's not actually that bad. A struct in Rust can be given a directive which tells the compiler to ensure it's laid out in memory the same way that the C compiler would. Calling into C and back does require the use of the unsafe keyword in Rust, but it's contained to a small part of the code and fairly easily managed. In the end, we developed a test framework that's able to test the behavior of MCUboot when power is lost at every part of the code where this can happen. It also tests multiple failures in a random manner. It can't test all of these because the number of possible occurrences is too large. These simulator tests allowed us to find and fix a number of bugs in the MCUboot code that could cause device failures on real devices if power was removed at those particular points in the operation. Now, in addition to the power down testing, we have added code to the simulator to test other features of MCUboot, and continue to work to bring the level of testing up to the point where every feature is tested. Rust, however, isn't a panacea. Although it does bring definite advantages to us, there were some hurdles to get over, and a few issues that we still encounter. One of the first things that we discovered is that the Rust test framework tries to run tests on as many CPUs as are available. Since MCUboot was originally written as embedded code, most of the state was simply stored in global variables, and this didn't work very well at all when it was invoked for multiple threads. Our initial workaround was simply to add a mutex that was taken by each test. This effectively made it so that only one test would run at a time. Eventually, we moved this global state into a struct that would be passed around. For the embedded builds, there is a single instance of this that is used, but for testing, it's allocated by the test framework in Rust and passed in. Now, cleaning the global state up in this way also helped us to make sure that when simulating a power loss, the global state is truly cleared and we didn't rely on values persisting across the reboot in memory. Now, the other primary difficulty we encountered with Rust is a lack of developers that are knowledgeable in Rust. What this means is most contributions to the C code of MCUboot don't come with simulator tests to test this functionality. We've mitigated this in two primary ways. One is to encourage contributors to at least try to build the simulator and make sure that their change doesn't break the simulator. Although CI will catch this breakage. We do run the tests. These contributions need to at least be able to run the simulator in order to be able to debug and fix the problems that it finds for them. The other mitigation is that at least 2 of the primary maintainers for the project are versed in Rust. Beyond just making sure that new contributions don't break existing tests, we've added numerous tests to test the new functionality as well. Overall, we find that using Rust to drive our simulation and testing framework benefits the project. One question that comes up from time to time, however, is whether the bootloader itself should be rewritten in Rust. Many of the advantages of memory safety would benefit this security-critical piece of code. Support for Rust on embedded devices is nascent. There are a few different efforts. Most have only a few boards that are supported, and the hardware that is supported on these boards is minimal. It could still be a worthwhile investigative effort to see if Rust would be helpful here, but it will be a while before there is a community around embedded Rust and enough device support for this to be a truly viable solution. Another possible way to support Rust on embedded targets would be to port the Rust runtime to an existing RTOS such as Zephyr. The RTOS would still be written in C, and the application would call into it from Rust. The memory safety improvements would be seen, however, in the bootloader. So an important consideration when thinking about another programming language is whether this is worth doing. There's kind of an ongoing joke, which is not really a joke, about the tendency people have when learning Rust to want to rewrite their project in Rust. Interestingly, at least, once there's good embedded support, MCUboot may be a good candidate for that. It isn't too large of a body of code, and it's code that would really benefit from the features that Rust brings to the table. Realistically, a Rust bootloader would probably be a separate project, possibly sharing data formats and algorithms, and could have the opportunity to grow and develop on its own. Thank you very much.